Good morning. My name is Rajesh Prasad. I'm working as professor in CSE department at Ajay Kumar Garg Engineering College, Ghaziabad. Today my topic of the lecture is complexity and recurrence relation. I hope you are aware about complexity, and let us see the overview of the lecture. And I'm going to talk about analysis of the algorithm, and then recurrence relation, type of recurrence relation, and various solutions to the recurrence relation. So let's define the complexity of algorithm. As all of us know that complexity of an algorithm is amount of time or space. If we are talking about time, we will refer the time complexity. If we are talking about space, we will refer the space complexity. So this is actually complexity of any algorithm is actually amount of time or space required to execute the algorithm. So it is generally function of size n, and for example, suppose fn is 2n plus 3. So that means size of input is n. So this is linear in nature. And another example can be like fn is 2n square plus, let's say, 3n plus 5. So complexity of this algorithm is quadratic in nature, where n is size of the input. So we can write also that if algorithm is not taking any time, this can be constants, which is denoted by 1. So this algorithm will not take any time, or it will take time every time, same time. Every time it is running, it will require the same time. So complex algorithm can take constant time as well. So how to analyze the algorithms? So there are two type of procedure. First one is iterative procedure. Second is recursive procedure. So iterative procedure involving loop actually, and recursive procedure involving recursions. So I'm going to talk about both the types, like iterative as well as recursive procedure. So iterative procedure, while analyzing the algorithm involving iterative procedure, will focus on the complexity of loops. Generally, focus is given on the loops. So rule number 1 is saying that complexity of data type declaration is always 0. For example, if we write a program, let's say main, right? And if we write a program main, and if we declare a variable, let's say integer I, right? So its time is going to be 0, because no compiler is going to read this data type actually. Same thing, type declaration. If you define a function prototype, let's say integer f, and let's say integer and integer. Suppose this is your prototype, right? So its time is also going to be 0, because compiler is not going to read this line. On the other hand, if you define integer I equal to 0, this is involving the assignment. So time will be constant. Any assignment statement is always taking constant time. Clear? So complexity of any data type or type declaration, prototype, data type, any kind of declaration is 0. Complexity of a statement executing constant time is always going to be 1. And any assignment statement is also going to be 1. So complexity of a loop executing n times is going to be n. This is the major concern. Loop is major concern in the iterative procedure. So for example, consider this program I is 1. So it is assignment statement, its complexity is 1, and this is our loop for I1, I less than or equal to n, and I plus plus. This is running n plus 1 time. Let's understand why it is running n times. So actually loop variable over here is I, right? So I, let us form a progression on I. Clear? So I will be at the beginning 1, then I will be 2, up to and so on. It is going and it will terminate. It is going up to I and it will terminate when I equal to n plus 1. Clear? Because it is executing up to n. So I equal to n. And now this is making arithmetic progression 1, 2, 3 up to I. So what is ith term of this arithmetic progression? You see, Tn is nth term in arithmetic progression a plus n minus 1 into common difference. This is nth term of arithmetic progression. So if I am interested in ith term of this arithmetic progression, first term is 1 and then I minus 1 into common difference. Common difference of this sequence is 1 and this is going to be equal to n plus 1. Clear? So now 1 plus I minus 1 equal to n plus 1. So implying that I equal to n plus 1. So that is why I am writing n plus 1 over here. So, you know that body of loop is always running one less than the loop itself. Suppose n is equal to 3. See this 1, yes, 1 less than or equal to 3 running one time. I become 2, print I 1 and I become 2, 2 less than or equal to 3, yes, running 2 time, printing 2. I become 3, yes, running 3 time, print 3, then I become 4. It is going to be tested over here. I become 4, 4 less than or equal to 3, no. So this is not going to be printed over here, right? So that means body of any loop is always executing one less than the loop itself. So now this was running n plus 1 times, so this is n and times print is a constant statement. So this its complexity is 1. So it will be n times 1. So total time will be 1. Total time, if I am interested in adding them, 1 plus n plus 1 plus n. So this is actually 2n plus 2. If we can approximate by big O notation, it will be big O of n. So this is how we are going to calculate. So suppose on the other hand, I'm like increasing in the form of I equal to I plus 2. What will happen? What will happen again? Again, let us form progression on I. I is 1. Then next is 1 plus 2 become 3, right? Then I become 5 and then 7. It will go up to I and it will fail if I equal to n plus 1. Same situation, right? So now this is a plus I minus 1 into common difference is 2, making it n plus 1, right? So now 1 plus 2i minus 2 equal to n plus 1. So 2i minus 1 is n plus 1. So implying that 2i equal to n plus 2, right? So this implies that I equal to n by 2 plus 1, right? So where n by 2 is like floor or ceiling function. See this? So that means in this situation, this is 1, right? And this will be n by 2 plus 1. Clear, class? And this is loop body, so it's going to be n by 2 plus 1 minus 1. So this will cancel out. So what is total time? Total time will be 1 plus n by 2 plus 1 plus n by 2. So this is actually the running time of the algorithm. So this is n by 2 is n. So this is n plus 2. This is running time, which can be approximated as big O of n. So this is actually done by, see this. So suppose n equal to 3. So in this situation, I is 1, right? So one time print 1, again I become I plus 2. So this is like 3, yes. I become 3, then again it will increment 3 plus 2, 5, and on 5 it is going to fail. So that means it is tested 3 times. Let's understand it. 3 by 2. 3 by 2 will be 1.5. So we are going to get this ceiling function over here. So that 1.5 can be approximated to 2, and now this is 2 plus 1, 3 times. So actually this is how we are going to calculate. This is ceiling function, not a floor function. So let's understand another example. So this is good example, and this is known as logarithmic loop. See this? We are not incrementing in the form of plus plus. I am incrementing in the form of multiplication. So what will, again, procedure is going to be the same, right? We just apply the arithmetic progression or geometric progression. In this case, we are not going to get arithmetic progression. We are going to get the geometric progression, right? So let's understand how it is going to form the geometric progression. I is 1, and then 2, then 4, 2 times I, then like 8. Every time we are incrementing in the form of 2, and then 16, and it will be I, and it is going to fail when I reach to n plus 1. Procedure is going to be the same actually. So now this is not arithmetic progression, this is a geometric progression. As we know that the nth term of geometric progression is AR n minus 1, where R is common ratio, A is first term, right? So if I am interested in ith term over here, ith term is 1, right? And common ratio is 2, 2 by 1 is 2, 4 by 2 is 2, common ratio is 2. I am interested in I minus 1th term. This is equal to n plus 1. Clear? So now this implies that 2 to the power I minus 1 is n plus 1. So I minus 1 will be log of 2 n plus 1. This is how we are going to calculate, right? So now I will be log of 2 n plus 1. Again we are interested in the ceiling function. I am not interested in the floor function. So this is plus 1. So that is how it is going to be like its time is constant 1, and its time will be logarithm of log 2 n plus 1 plus 1. This is how we are going to get it. So next is like print, as I know that, as we know that its loop is always executing 1 less. Body of loop is always executing 1 less than the loop itself. So its running time will be log 2 n plus 1, and then plus 1 was the loop and minus 1. So after adding all the time, we will see that if you just add all the time, what will be the time? Total time of the algorithm will be Tn is 1 plus log of 2 n plus 1 plus 1 plus log of 2 n plus 1. So total time is actually equal to ceiling of log 2 n plus 1. This is 2 and plus 1, which can be approximated as log n base 2. So this is an example of logarithmic loop. Same thing we can also do, like in the case of logarithmic loop, you can also start from n, I greater than or equal to 1, right? And I is I by 2. If you change this line to I is I by 2, this is also going to give the logarithmic loop. Suppose first one it will be n, then again it will be going to n by 2, then n by 2 is square. This is going to be computed and it is going to fail when I equal to 0. This fail when I equal to 0. So same computation we can get to find out the value of I. So let's consider another example of the double loop. This is also important. Generally we use this double loop in the case of matrix multiplication and another places. So you see here I 0 0 less than m. Same technique, it is running 0 and see, let's say m is equal to 3. So 0 and then 1, then 2, up to and so on. It is going to fail when I equal to m. So same thing, arithmetic progression, a plus I minus 1 into common difference. Common difference is going to be 1 equal to m. So I minus 1 equal to m. This means that I equal to m plus 1. So right. So that is how it is coming, m plus 1. And this is body of this upper loop. See this here, body of the loop, and it is also running n plus 1 time. And since this is body of loop, so this will be running times m. This is running times m. This become body of loop. So itself times m. And next is this like printf. This is body of this loop. So this is running, this loop is running n plus 1 time. It is n, right? And now this is also body of this loop. So this is going to be traverse up to the upper side. So now this is also running m plus 1. So this will take n because of this line, and then because of this line it is m. So you are going to print hello m times. Let's have an example that m is 3 and let's consider n equal to 2. Let's find out how many times hello is going to be printed. Okay. I is 0, 0 less than 3. J is 0, 0 less than 2. Correct. So print hello. Hello is printed one time. Then again J is 1, 1 less than 2. Correct. Again hello is printed. 2 times hello is printed. Now j equal to 2, it fails. Then and so this is corresponding to I equal to 0. 2 times it is printed. Again I become 1. I become 1. Yes, I become 1. So again j 0, 0 less than 2. Correct. So we are printing hello and again we are printing hello. Clear? Yes. So again I become 2. So I become 2. So I is 2, 2 less than 3. Correct. Again j is 0, 0 less than 2. Correct. And so it is again going to be printed 2 times. So how many times hello is printed? 6 times. Hello is going to be printed 6 times. Same thing here. N is 3, right? And n is 2 and m is 3. So this is going to be printed 6 times. So there is no difference in the calculation. So let's understand the same situation when we are involving the 3 loops, right? So for I equal to 0, I less than m, I plus plus, let's say this. And then for j0, j less than n, j plus plus, let's say this. And again for k0, k less than p, k plus plus, and let's say this is hello, print hello. Suppose I am using this print hello. So this is closing here, this is closing here. So question again, same thing. So what is time of this? Its time is m plus 1. It is going to be executed m plus 1 times. And same thing here, this is n plus 1 loop itself, and this is body of the upper loop, right? So this is n plus 1 into m. And now this is again, its time is p plus 1, and now this is body of upper loop, so it is n, and now this is body of upper loop, it is m. It is going to be multiplied by m. Same thing, what is time of this line? You know, this is p, right? And p, and then this is loop body of this, it is n, and then it is body of m, upper. So this is p times n times m. So that is how we are going to calculate the double loop. So this was all about the program involving iterations, involving loops. What about program which is involving the recursion? So if a program is involving recursion, we are going to take help of the recurrence relation. So for example, everybody, we know that Fibonacci sequence. Suppose this is 0, 1, 1, 0, 1, and then 1 plus 1 is 1, and then 2 plus 1, 3, 3 plus 2 is 5. So what is recurrence relation for this Fibonacci sequence? If we talk about this is 0 if n equal to 0. This is 1 if n equal to 1. Otherwise, fn minus 1 plus fn minus 2 if n greater than 1. This is Fibonacci sequence, right? So, of course, if we are writing the program using iteration, so this is iterative program. Initialize the first term 0, second term 1, and then print them A and B. Start from this is 0 term, 1 term, then 2 term. Start from the second term, right? So now while I less than n, this is like, it is going to run n minus 1 time. C is temporary variable, take them A plus B, added it, print C, and then A is getting B and B is getting C. So this is iterative program. See this 0, 1, 1, 2. So this is going to be A and this is going to be B, right? And now this is going to be C. So once you start from the second term, C is A plus B, yes, added. And now there is a shifting. After printing, A is here and B is here. A is getting B, B is getting C. And it will continue. So if we look at iterative complexity of this program, it is 1, it is 1, it is 1, it is 1. Constant time assignment statement. So now this is running n minus 1 time. Same method, starting from 2. If you start from 2, then 3, then 4, up to and so on, it is failing when I equal to n, right? So 2 plus I minus 1 into common difference equal to n, right? So this is 2 plus I minus 1 equal to n. So I plus 1 equal to n. So from here, I is n minus 1. That is how we got I equal to n minus 1. So you know that this is body of the loop. So this is n minus 2. This is also n minus 2. Everybody is going to be, because all of them, they are assignment statement. Their own complexity will be constant. So it is not going to affect this. Otherwise, you can write 1 times. You can write 1 times. You can write 1 times and you can write 1 times, right? So if you add all of these terms together, we will get that complexity is linear in nature. So, but what about if you want to implement this procedure? Like, see this procedure. So what will be the time of recursion? Recursion is not involving loop. So in this situation, if you write fn like any program which is involving recursion, so we have to form a recurrence relation to solve the question. So any program which is involving recursion, we have to form a recurrence relation, right? So see, for example, if I'm writing Tn is Tn minus 2, 1 plus 2, definitely with boundary condition at T0 equal to 1. So this is an example of recurrence relation, because if you are interested in calculating, let's say T3, so definitely nth term is going to be computed in terms of the previous values, right? So T3 is going to be T2 plus 2, definitely. And now T2 is going to be calculated by T1 plus 2 and plus 2, right? So T1 is going to be calculated by T0 plus 2 plus 2 actually, and then plus 2. So definitely you have boundary condition T0 which is equal to 1. So 1 plus 2 plus 2 plus 2 is making like 7. So that means this is an example of recurrence relation. While if you are interested in C, this Tn, it is not a valid recurrence, because if you are interested in calculating T3, right? So T3 should be calculated in terms of the previous value. So this is 3 times 3 divided by 2 plus 2. So this is actually T9 by 2. So this is more than 3 actually. This is more than 3. So this is not a valid recurrence, right? So in order for a recurrence to be valid, nth term should always be expressed in the terms of the previous values, right? Otherwise, if you are writing nth term and it is going to be expressed in n plus 1th terms, it is not going to be valid, because it is not going to be terminated. So if you are interested in solving this type of recurrences, we have so many methods. So number one method is like method of homogeneous recurrences, right? So suppose this is your recurrence A0 Tn plus A1 Tn minus 1 Ak Tn minus k. So we need to write into this form. So you see, for example, Fn is Fn minus 1. So this is going to be computed by this. So if you solve this by the method of homogeneous recurrences, you will get value of Fn as this. Fn is going to be written as 1 by root 5 this. After solving it, there are many methods for, like, for example, if you use homogeneous recurrences, this can be solved by Fn minus 1 minus Fn minus 2 equal to 0. This. So assume that Fn is x to the power n. So x to the power n minus this minus xn minus 2 equal to 0. Taking lower order term outside, you will get x square minus x minus 1 equal to 0. This is not going to be 0, as you will get trivial solution. So this is going to be 0. So x square minus x minus 1 equal to 0. You can solve value of x from here. X1 will be 1 plus root 5. After solving this, it has 2 root, and x2 equal to 1 minus root 5 divided by 2. This is going to have 2 roots, x1 and x2. So after computing them, and you see Fn will be written as C1 x1 to the power n plus C2 x to the power n. And we have the terminating condition. You know that in Fibonacci sequence we have F0 0 and F1 as 1. So if you put it over here, F0 0 1 0 and F1 1, you will get that value of C1 from here. C1 will be 1 by root 5 and C2 will be minus 1 by root 5. So you just substitute the value of C1 and C2, you will get this recurrence. So from here directly, you see, if you are interested in value of F0 from here, you just put the direct, no need to be going back and forth. F0 will be 0 minus 0, so this will be 0, right? Same thing, if you can put f1 over here, you will get the value as 1. So direct, if you are interested in f10, you just put value of 10 over here. No need to be going back and forth. It will compute the value of f10. So this is the advantage of solving the recurrences, right? So there are methods that if right hand side is not 0, there is method to solve it, but that is beyond the scope of this course. So what we did here today, we started with like iterative procedures, and then like how to solve it, and we saw that okay, loop is like running n times, and constant, they are taking constant time, like then we are able to understand that how to solve the like recurrences using recursion. So that's all today. We'll continue with the recurrence relations in the next lecture. Thank you.